All right, salut tout le monde. Welcome back to the differential geometry reading streams. I'm Anthony, obviously. This is episode, I believe, 37 now, where we've been reading Differential Geometry by Erwin Kreisig out loud. Today I'm about to finish chapter 7 from this book, which comprises two sections essentially, which are discussing in further detail the connection of the Levi-Civita. And the previous episode basically derived that. And as I mentioned in the previous last few episodes, really this chapter has been really all about Riemannian geometry. And a lot of what came before, okay, maybe not geodesics obviously, but all of the stuff about the theory of surfaces, theory of curves, that could all be lumped into what's called smooth manifold theory nowadays. This has all been Riemannian geometry. But also I mentioned over the course of like 10 minutes, which I'm going to compress down now into a minute or less now, hopefully. This book basically had 3 editions. First edition was in German, and that was the first edition. Second edition was the first English translation of this material, which came out in 1959. And then there was a third edition, which came out about 10 years later, I think in 68 or 69, as a book called Intro to Differential Geometry and Riemannian Geometry, which basically addressed a lot of what even reading today are like the major criticisms of that second edition, which that second edition was reprinted in 2008 to make this Dover publication of that book by Erwin Kreisig. So last episode, I was reading the equivalent section as would be from the Differential Geometry Dover book, but what's from the Intro to Differential Geometry and Riemannian Geometry, the like third edition, third iteration of this material from Erwin Kreisig, rest in peace, right? Because, for example, like one of the main criticisms you could leverage against this book is that when it discusses the connection of Levi-Civita, supposedly in this book, it doesn't mention connection at all. It just refers to the displacement of Levi-Civita, which is like the, I guess, like tensor or like vector field associated with the connection of Levi-Civita, but the connection itself is more like a rule, perhaps. But obviously, as goes with all the other episodes, a lot of this material, it's the first time I'm reading it, so my articulation of what it all means back to you might not be as polished the first time around. But if you stick around, like, comment, subscribe, then in a few episodes it'll probably be way more clear. There'll probably be like a consolidation review episode that is hopefully more popular, any day now, any week now on all this stuff, or maybe not, who knows. But anyways, so yeah, I'm going to read these sections from the third edition of the book, if you will, because it actually emphasizes the connection of Levi-Civita, which is, more or less like the modern way we do things now. This book, as it came out in 1959, it sort of has one foot in the quote-unquote classical differential geometry, one foot in the modern, because modern, people would put the demarcation point somewhere around 1950. So this is very much in that gray zone, especially when this is writing at the undergrad level. But still, this guy, he wants to be comprehensive still, or, have good breadth of his material. Anywho, let's get into it. Section 79, Properties of the Connection of Levi-Civita. In the case of Cartesian coordinates in the plane, the Christoffel symbols are identically 0 and 78.5 prime, which from the previous section is capital D A superscript J lowercase dt is equivalent to A dot superscript J plus A superscript P, then times Christoffel sub Pi superscript J, then times u dot superscript I equals 0, where j is either 1 or 2. That reduces to a dot superscript j equals 0, where j is equal to either 1 or 2. Then the components of the displacement of a vector are constant, and the connection is independent of the choice of a curve. In other words, in this particular case, the connection of Levi-Civita becomes identical with the above elementary connection. More generally, the following theorem holds. Theorem 79.1, independence of path. The connection defined in the previous section, which I'll just flash it on screen right now, is independent of the choice of a curve capital C, again see above, if and only if the surface, or see the previous episode 36 rather, if and only if the surface under consideration is a developable surface. And I talked about developable surfaces, I think, in episode 21, which is roughly, I think, section 52 out of this book here. The proof is as follows. If the solution of the differential equations of the connection of Levi-Civita is independent of the choice of the curve capital C, then a superscript j and then with a subscript of comma I is equal to 0. From 76.7, which again I'll put on the screen right now, we see that the corresponding integrability condition is a superscript t then times, I'm assuming that this is a Riemann curvature tensor, capital R superscript j sub tki is all equal to 0, where j is equal to either 1 or 2. If solutions of the above relation 79.1 corresponding to arbitrary initial conditions should exist, then the other above expression 79.2 must be valid for arbitrary a superscript j. Hence, the coefficients of the tensor capital R superscript j sub tki must be 0. From this, as well as from relations 41.7 and 41.15, which I'll put those on the screen right now, it follows that capital K equals 0, that's Gaussian curvature is equal to 0, and the surface must be developable, for which refer back to theorem 55.2. So if we have capital K equals 0, Gaussian curvature equals 0, then the surface or manifold is isometric to n-dimensional Euclidean space, basically, or like a Euclidean plane, n-dimensional Euclidean plane. Conversely, in the plane, the displacement does not depend on the choice of a curve capital C. Again, from the differential equations of the connection of Levi-Civita, we see that the connection of Levi-Civita is an intrinsic property of a surface, namely that it depends only on the first fundamental form. Since every developable surface and a plane are isometric, the result follows. This completes the proof. Furthermore, since the connection of Levi-Civita is an intrinsic property, theorem 51.1, hopefully I'm flashing that on the screen right now, yields the following result. And again, I will say really quickly that all of these are in the corresponding sections of the differential geometry book, but these little descriptors on the theorems like isometry, geodesics, scalar product that we see here are actually missing in this copy here, the second edition, if you will, of differential geometry. So that's why I partly chose reading from this book, the third iteration for these sections. So hopefully you appreciate that. But anyways, theorem 79.2, isometry. If vectors are parallel with respect to a curve capital C on a surface capital S, they are also parallel with respect to the image of the curve capital C under an isometric mapping of the surface capital S. The displacement is independent of the special choice of coordinates on a surface, since the left-hand side of the differential equations of Levi-Civita forms or is a tensor. We come to theorem 79.3, geodesics. The tangents to a geodesic capital G are parallel with respect to capital G in the sense of the connection of Levi-Civita. We have a little quick proof, which is as follows. If we set a superscript j equal to du superscript j ds in the differential equations of the connection of Levi-Civita 78.5, we obtain 43.2, which I'm going to put on the screen. I'm being a little bit lazy with this one because I don't want to scroll away from where I am right now. And the correspondence between the section enumeration of the second edition, Dover edition, reprinting I have in my hand, and what's on the screen, the third iteration, it's a little bit off. So I don't want to, double down on anything and be totally wrong. Anyways, Because of the property characterized in this theorem, the geodesics are also known as autoparallel curves. And we're a little bit thick on the commentary so far, but autoparallel curves are another topic which is not in the second version, the Dover reprinting, which came out in 2008, which it's the physical copy I keep on grabbing, but it's introduced to sort of like flesh out the Riemannian manifold extra bit of theory that was kind of like missing or was vague in the second edition, which was reprinted in 2008. It's kind of confusing with that, right? Like the second edition that was printed in 1959 that then got blown up by Dover in 2008 is not as good as its final form. It's not the final form, but it's like, this is what everyone's got a hold of because of Amazon and capitalism, right? Because it's super cheap. The Intro to Differential and Riemannian Geometry, the third edition, is like $50. It's like, why would you shell out $50 if you're some grad student? Because that could just get you something like John Lee's Intro to Smooth Manifolds, which you're actually probably going to need for a class, right? Anyways, moving on. Autoparallel curves are in this third edition, that's all I'm saying. Theorem 79.4, scalar product. If two vector fields A superscript j in terms of parameter t and B superscript j in terms of parameter t are the displacements of two vectors A superscript j of t naught and B superscript j of t naught along the same curve, capital C, which is denoted by U superscript I, which is parametrized by a function U superscript I in terms of the parameter t, where I is either 1 or 2 on a surface capital S, which is parametrized as a vector x in terms of coordinates u1 and u2. Those are contravariant indices on the u coordinates. Then, at each point of capital C, the curve, the scalar product g sub jk of t and a superscript j of t, then times b superscript k of t, has the same value. That was actually a little bit fun to read. The proof is as follows. The derivative of this scalar product with respect to the parameter lowercase t is partial g sub ik partial u superscript m then times u dot superscript m then times a superscript I then times b superscript k plus g sub jk then times the quantity a dot superscript j then times b superscript k plus a superscript j then times b dot superscript k closed quantity. We show that it is 0 using the previous expression for the differential equations of the connection of Levi-Civita, which are referenced by 78.5 prime here in this book. We have that g sub jk then times the quantity a dot superscript j then times b superscript k plus a superscript j then times b dot superscript k closed quantity equals negative g sub jk then times quantity a superscript I then times Christoffel sub im superscript j then times b superscript k plus a superscript j then times b superscript I then times Christoffel sub im superscript k closed quantity then times u dot superscript m, which then is equal to the negative quantity a superscript I then times Christoffel sub im k then times b superscript k plus a superscript j then times b superscript I then times Christoffel sub imj closed quantity then times u dot superscript m. This then equals negative a superscript I then times b superscript k then times the quantity Christoffel sub imk plus Christoffel sub kmi closed quantity then times u dot superscript m. From this and another statement which is on screen now, 39.2, the statement follows and this completes the proof. Setting b superscript j in terms of t equal to a superscript j in terms of t in the previously stated scalar product theorem 79.4, we immediately obtain theorem 79.5, which is about the length of a vector and angle with respect to the connection of Levi-Civita here. A displacement a superscript j in terms of s, the arc length, of a vector in the sense of the connection of Levi-Civita has constant length. The angle between two such displacements along the same curve is constant. Consequently, if two vectors in a surface capital S which are bound at the same point capital P of S and have different directions undergo a displacement along the same curve capital C, they can never at any point of capital C simultaneously assume the same direction. A similar statement with respect to the length follows also from theorem 79.5, which I just read. We see that the correspondence between all the vectors in the surface capital S at the point capital P and their displacements along the same curve capital C at a point capital Q of the same curve capital C is 1 to 1. In this way, the vector space of the vectors in the surface capital S at the point capital P is mapped onto the vector space of the vectors in the surface capital S at the point capital Q in a 1-to-1 fashion. This mapping is an isomorphism, that is, if A superscript j at the point capital P is mapped onto A superscript j at the point capital Q, and B superscript j at the point capital P is mapped onto B superscript j at the point capital Q, then the vector C superscript j at capital P is equal to lowercase k times A superscript j at capital P, then plus lowercase l times B superscript j of capital P is mapped onto C superscript j of capital Q equals lowercase k then times A superscript j of capital Q plus lowercase l times B superscript j of capital Q. Here, lowercase k and lowercase l are constants. And now we are at the last section of the chapter on absolute differentiation and connections on surfaces, or also displacements on surfaces. Depending which edition, the concepts are interrelated. It's just, like I said, we're emphasizing connections rather than displacements. Anyways, section 80. Geometrical interpretation of the connection of Levi-Civita. We know that the connection of Levi-Civita is an intrinsic property of a surface. Nevertheless, we may use the embedding and obtain a geometrical interpretation of the connection on surfaces embedded in R3, three-dimensional Euclidean real space. Our consideration will be based on the following theorem. Theorem 80.1, connection on surfaces in R3. Let capital C be a curve on a surface in Euclidean space R3. Suppose that vectors along C are given and are differentiable functions of the arc length lowercase s of capital C. Then these vectors are parallel with respect to C in the sense of the connection of Levi-Civita if and only if the derivative of these vectors, regarded as vectors in R3, with respect to arc length lowercase s is the null vector or is normal to the surface. The proof is as follows. Every vector A superscript k in a surface, vector x in terms of u1 and u2, considered as a vector in the embedding space, can be represented in the form vector v equals A superscript k then times vector x sub k. Differentiation with respect to the arc length lowercase s of the curve capital C yields vector v prime equals A superscript k prime then times vector x sub k plus A superscript I then times vector x sub ij then times u superscript j prime. Using the on-screen expression 38.7, we obtain vector v prime equals the quantity A superscript k prime plus A superscript I then times Christoffel sub ij superscript k then times u superscript ji closed quantity then times the vector x sub k plus A superscript I then times b sub ij then times u superscript j prime then times the vector n, which is a normal vector. If the vector v prime is the null vector or has the direction of the normal to the surface, then the expression in the parentheses must be 0, that is, the differential equations of the connection of Levi-Civita is satisfied, and vice versa. This completes the proof. We shall now consider two surfaces, S1 and S2, which have contact along a curve C, that is, they have the curve C in common, and along C, common tangent planes and common normals, for which we can refer back to section 56. Applying the aforementioned theorem 80.1, we obtain theorem 80.2, which has to do with contact. Let two surfaces S1 and S2 have contact along a curve C. Then vectors in S1, which are parallel with respect to C, are also parallel with respect to C when considered as vectors in S2. These theorems characterize the connection of Levi-Civita from the standpoint of the embedding space. Since the connection is invariant with respect to isometric mappings, for which refer to theorem 79.1, which I just read in this video, we may use theorem 80.1 above to obtain in a geometrical fashion the displacement of a given vector in a surface capital S in three-dimensional real Euclidean space along a curve C as follows. We choose a developable surface capital D which has contact with the surface capital S along the curve capital C. Again, refer back to section 56, and map capital D isometrically into a plane capital E, for which refer to theorem 55.3. Then we displace the given vector along the image C star of C in the elementary sense and map onto capital S the surface, the vectors thus obtained. From the contact theorem 80.2, it follows that these vectors are parallel with respect to capital C, the curve, in the sense of the connection of Levi-Civita. We now come to an example, and there are a couple figures here which actually are still in, of course, the physical copy of the previous edition, second edition of differential geometry here. So we're not gaining or losing anything. Example 80.1, having to do with a sphere. Let capital C be a circle of radius lowercase r sub c equals r then times sine of phi on a sphere capital S of radius lowercase r, which we have here below. This is like a dunce cap. Getting attacked by my cat. Let a vector at a point capital P of capital C be given. For the sake of simplicity, we suppose that vector to be tangent to capital C. We displace this vector from the point capital P along the curve capital C back to the point capital P. The developable surface capital D having contact with S along C is a cone of revolution, or a cylinder of revolution if C is a great circle on S, for which again refer to figure 80.1. Hopefully that's juxtaposed on the screen here to save me from scrolling. The apex of capital D, the developable surface, is at the distance m equals r sub c then times the secant of phi, which is equal to r times the tangent of phi, from capital C. We cut capital D along the generator through capital P, the point that is, and bend it in a plane, as shown in now figure 80.2. Since C and its plane image C star have the length L equals 2 pi r sub c equals 2 pi r sine phi, the angle at the image of the apex is, referring again to figure 80.2 right here, beta equals a fraction with a numerator of 2 pi r sine phi all over a denominator of r tan phi, which is then equal to 2 pi cosine phi. Hence, the angle between the displaced vector and the tangent to capital C at the point capital P is lowercase delta equals 2 pi times the quantity 1 minus cosine phi closed quantity. This angle depends on phi, that is, on the choice of the curve capital C. In particular, lowercase delta equals 0 if and only if C is a great circle on the surface capital S. This surface is a sphere, rather, in this example, of course. Then the given vector and its displacement coincide. This agrees with theorem 79.3 because great circles are geodesics on S, the sphere, and the given vector is tangent to the curve, which is a circle, capital C, at the point capital P. And there you have it. That is the end of not just section 80 and wrapping up the second episode, part 2 here on the connection of Levi-Civita, but that also wraps up chapter 7 on absolute differentiation and parallel displacement, connection of Levi-Civita, displacement of Levi-Civita. It's a mouthful. I just, want to make sure that I put it all out there, that I say everything. That way, I come across as a thorough, detailed individual when it comes to this stuff. But you guys can think whatever you want. I just thought I would hop on and do one of these. The next chapter on minimal surfaces is the last chapter of the book. And yeah, let's just crank them out. Let's keep it rolling, and I'll see you guys in the next one. Peace.